Welcome to all of you to this webinar about non-intrusive code coverage with UDE. In this webinar, I will have a look at a more test-related topic, not debugging. The topic is how to get code coverage information for your performed tests from the debug tool. And what are the specific features of this functionality, and maybe also the differences between code coverage that is provided by validation and test tools compared to code coverage that is provided by a debug tool. Before I start, let me give you an overview of what you can expect. At the beginning, I will give you a brief introduction into the topic code coverage, especially for trace-based code coverage. Then I show you the features that we have in UDE for it. This contains the analysis functions as well as how to embed the code coverage feature in automated tests. And finally, I think it's necessary to draw your attention to a certain aspect when you're measuring the code coverage of your tests on optimized code. In fact, the UDE is not only a debug tool to find bugs, it is also a tool that supports you when you're testing software. The UDE provides a lot of features for that help you to execute automated tests on real hardware, for example. And this can be done using our software API that allows to use scripts for automated tests or to connect third-party tools to the debug tool. This topic about the software API, this topic was covered already in the previous webinar. If you are interested in and you missed it, a recording is available for this webinar, and we put the link on our website or the website of Hitex. You may know that a test alone is not sufficient, especially in the field of safety critical applications. If you are looking at the current standards, for example, the ISO 26262 for automotive applications or the DO 178 for electronics in aviation, then you will see that not only the test itself is addressed in great detail, but also the evaluation of the significance of the test and the test quality. One metric for evaluating and ensuring test quality is code coverage. Basically, the code coverage indicates how much code was actually executed, triggered by the test cases. If you look at this example here, we have a piece of code and we have a test case which is used as an input for this piece of code. You execute this piece of code and then you get a result set1, x1, and the result set1. And you see that only a piece of code, not the complete code, is executed, triggered by this test case x1. Then you need another test case, x2, for example. This leads into a result set2, which can be checked if it's okay. And you see we have another piece of code which is now executed, triggered by this test case x2. But there is something missing, so we need a third test case, x3, which finally stress the rest of the remaining application or the remaining code and results in a set 3, which may fail or not. And with these 3 test cases, we got a 100% code coverage. There are different levels of code coverage. The simplest one is the statement coverage, which gives you the ratio between the executed statements or instructions and or the statements or instructions in a module or in a function. But the statement coverage doesn't tell you nothing about conditions in your code. To ensure that also all the paths of a condition are tested, you will need at least a branch coverage. This gives you the ratio between the taken branches compared to the overall number of possible paths through your code. Path means in terms of the control flow of your application. There's a control flow graph. You may know that. Before we go further, let me emphasize that a very important point, that the code coverage tells you nothing about the software quality of your product. It tells you only about the test quality. So in this example, we show you that we have already a piece of code here, and for a complete statement coverage, it would be sufficient to use the test case X minus 7. So all the instructions are executed. It's good for now, but not enough. If you want to make sure that also all the not taken branch or the not taken path is triggered by the test, then you need another test case. For example, X is 7. So then we get a complete branch coverage of 100% with these two test cases. What we did here manually for measuring the code coverage and to evaluate the use test cases was that we executed the tests, 2 tests in this case. We observed the instruction flow, especially which edges of the control flow were executed. And finally, we evaluated and calculated the coverage with the result of 100% branch coverage in this specific case. The question is now how we do this observation of the code execution by the tool. We did it manually. We looked at the edges and counted the edges. And if you want to use a tool, then there are basically 2 ways possible. First, you can instrument the code so that the code observes the execution by itself. So a lot of test tools and verification tools on the market work like that. But this is very useful approach. You see, the great advantage of this approach is that you can test your application on your PC running a simulator or something similar. It's completely target independent. But if you change to the real hardware, then I guess you get some undesirable results. You have a changed runtime behavior, obviously due to the additional code that you get with the instrumentation. You get maybe a changed code size as well due to the instrumentation, and possibly a different memory layout because the collected data, the counters for the edges, for example, need space at the target memory. And so maybe you get a different memory layout. In the end, you have to be aware that the code under test is not the code that you will use later in the product anymore. Then I assume that you will never load a instrumented code on your product and run it in the field. The second approach to get the data for the calculating the code coverage is to use trace, hardware trace provided by some of the used microcontrollers. This is a completely non-invasive method. No code instrumentation is required, and so you have no influence on the runtime behavior nor on the memory layout. The code under test is the same code that is running on your product later in the field. But this approach gives you only a coverage at object code level because you are observing the executed machine instructions and nothing else. And this may be a disadvantage, but it could also be an advantage in our opinion, because you get the coverage for your tests that are executed on the real code, on the real hardware. And this is in most cases also a optimized code optimized by the compiler, which is then also the final production code. But the real drawback here is that in some specific cases and with highly optimized code, you miss some information about the control flow inside the code, which is in fact needed by the debug and trace tool to calculate a correct control, calculate a correct code coverage. And if you do not have this information available, then the coverage results may be incomplete. I'll come back to this specific case later. It has to be added here that due to the limited amount of trace memory, either on the target hardware, if you have an on-chip trace memory, or inside the tool, this limited amount of memory is the reason for the need of partitioning of the measurement for the code coverage, and also partitioning your test cases or your test runs. Typically, test tools, for example, are testing only one function at the same time, so there is a partitioning, yeah, you have to accumulate the results then after that. This can be done automatically by the test tool, or if you do the tests manually, or automatically by scripts, then you have to do this also manually and take care of that. Okay, then let's have a look at the UDE code coverage features and also how it looks like in the tool. At first, some of the features here. The trace-based code coverage that UDE provides can calculate two levels of code coverage: statement coverage CO and also branch coverage C1. The coverage results are presented in a dedicated code coverage window that allows to look into the coverage at several levels of detail, for example, at function level, which is interesting to get an overview. Then you can look into the function and get the C level cover or C statement level coverage. And also, if you want to look deeper into this, then you can get the object code level or the code coverage for the object code or the machine code. Reports can be generated to document the achieved coverage levels of the tests. For this purpose, there are different output formats available. The UDE code coverage functions can also be accessed by our software API that UDE provides. It is called the UDE object model that supports scripting and also connection or connecting third-party tools to the debug tool. The code coverage feature is available as soon as you have licensed the UDE trace feature, which is an add-in. And of course, you have to purchase this in addition to a base debugger license. Okay, and then let's jump to the UDE. And let me show you the features. I have already prepared a workspace with a running application. The application is a simple clock, and we want to test the functions of this clock, especially, of course, the corner cases where carryovers occur at the end of the minutes, the hours, and the days. You see here on the watch window the clock state, we call the tens of seconds, the minutes, and the hours. So the application is running, and before we perform the tests, we have to prepare the trace system for recording the executed instructions and for measuring the code coverage based on this trace. I'm on a AURIX microcontroller, so the AURIX microcontroller provides a trace system called MCDS, and for the MCDS we have a trace configuration tool which is called the Universal emulation configuration. So this is basically the tool that allows you to create a trace task for specific measurements. In this case, it's very simple. On the left side, we have a library of predefined trace configuration blocks. And for this specific case, we want to trace only a subset of the target application. We want to trace only the update function of the count of the clock. This update function is divided into several parts. I can show you this here. This is not the right one. This is the update clock function, and it calls every 10 milliseconds this update tens of seconds functions, and this calls at the end of 1 second the update second function, and so on. So it's a nested call hierarchy. So let me go back to the configuration tool and put it outside so it makes it a little bit better to see. The first thing we have to do, we have to set up the trace on the target hardware. We have to define how much trace memory we want to spend. 256 kilobyte should be enough for that. Then when the trigger defines when the trace is started or the trace is stopped. The pre-trigger means trace is started as soon as the trigger condition occurs, whatever the trigger condition is. And we have also post-trigger, which means that the trace stops once the trigger condition occurs. And we are on core 1, so I select core 1 for the trace. And then we need a condition to start and stop the trace recording. And we use this block here, which allows us to define a start condition and a stop condition in form of a code address or a code symbol. So I select core 1 here, core 1 update clock. Once we enter the update clock function, trace should be enabled. And once we return from this update clock function, trace recording should be interrupted or stopped. and because of the pre-trigger, we will record multiple executions of this update clock function and all the other functions that are called from that. Let me say that it is always a good idea for testing and also for parallel measurement of the code coverage that you define such a suitable cutout of the application. And here in this case, it's very simple. We observe only the execution of the core one update clock functions and all the called functions here. Okay, then we are finished. We can configure or compile this this configuration to make sure that is loaded to the target system, and then we can start the trace recording. So you see, okay, the recording is active, and because of the slow clock in this term here in this example, we got also a slow progress here. So I stop this manually, and then you see automatically the code coverage is calculated for the execution of this core one update clock. And you see we have only a partial covered code coverage here or execution of all the called functions here because we didn't specify any specific test cases for all the code that is executed. If you want to document the results of your code coverage, then you can create a report in different formats, for example, HTML, XML, CSV, or text format. You need to specify the location for this. Let me use the sample directory, and you can specify a name for the report or a pattern to create multiple reports at once. For example, module name and also date time with the underscore. Press OK. Okay, and then the report is created in the HTML format. And you see, you can now you see all the information that you need, and you can also click on it and see the details. You get also all the details in the code coverage window as well. For example, I've opened the core one. We see all the functions which are traced and for which we can calculate a code coverage result. We can, for example, open one function and get the statement coverage for C lines here. You see, okay, we have here a if statement which is 100% have a 100% statement coverage, but only a 50% branch coverage. So one of the paths for this if statement is not covered. We see here which one. The reset of the seconds once we finished 1 minute is not covered, so we need a test case for this as well. And you can also look at the object code level for statement as well as also for the branch coverage. Here you see the jump or the branch instruction, which was never taken. Only the fall through pass was taken here in this specific case. What else? Statement coverage and MCB means machine code branch coverage. This is the branch coverage on machine code level, and the line coverage is the is the statement coverage on the different levels of details, starting from core, function, C statement, and machine code statement. Then we have the start and the end address of the code, which is executed on line basis or on the machine code basis, as well as information about the C files and as well as the line number. Okay, from here you can also jump, for example, to the code window or the program window, and here you see on the left side these green marks, and sometimes you will also see yellow marks, which indicates the statement coverage of this specific source code line, or if you use the mixed mode, then also the statement coverage of the machine code line or the object code here. Green means 100% code coverage. Yellow would mean not 100%, but seen in the trace. This happens typically if you have a if statement with a combined condition. So where the one condition is evaluated, for example, and the other condition not, because of a, for example, AND combination where only the first condition has to be evaluated, and if it's false, then you can omit the second subcondition of a combined condition. Okay, this is not a very practical example, because in practice you will do the code coverage based on automatic tests. And this feature I'd like to show you next. For that, I have prepared a Python script. So where is it? Here is it. A Python script using the UDE object model. I said before that all the topic about Python and scripting with UDE was already covered by the previous webinar. So I keep the first things short. I use for demonstration the IPython Jupyter Notebook, which is a browser application which allows us to interactively develop Python scripts and execute it step by step. For example, in this, we have here cells which can be executed at once, and then the execution rates for the next cell. You can do this step by step. It's a very cool tool, and I think I put the link to it into the slides, which will be shared then after the webinar by Wolfgang as a PDF file. The first few cells here prepares the script, connects to a running UDE instance, gets the workspace, which is basically the debug session, and then we get the core debuggers for core 0 and core 1, which is needed for run control, and also to get a breakpoint object for the core 1 for our function that should be tested. So let's execute these cells here. So now we get all the things we need for the test. Core 1 debugger Core 0 debugger. Then we need the trace, which is also available as a workspace property. Here you see we use MCDS trace for the Infineon AUX microcontroller. We need breakpoints, and we made it go so the application is running. Then we want to prepare our tests, and we want to stop at the next execution of core 1 update clock, which is the function that should be tested. So once we stop, we prepare the trace. From the trace object that we got from the workspace, we ask for the UEC object, which is for configuring the trace, and we load a predefined trace configuration. It's pretty much the same that I used in the test before. I can show you the trace configuration that we are using here for this test, which is this one. The only difference here is that we do a post-trigger trace. That means we only observe one iteration of this core 1 update clock. And if we return from this core 1 update clock function, then the trace is stopped automatically. This is the only difference to the other configuration that we used before. So we configure, and then we need the code coverage object, which is a part of the trace use case automation manager that we got from the trace object, and we want to access the code coverage for core 1. Execute this, and then we clear everything, and because we have already results here in the window, and we set some properties here. This accumulate property means that we expect to test with multiple runs, and we want to accumulate over all the runs the code coverage calculation. And we want to do a manual control, not a manual control. We want to calculate the coverage automatically right after the trace has been stopped. Then we need the test vectors. I prepare a struct or structure containing the test vector and a good vector for the test. So that we can compare it after the test and say, okay, test passed or test failed. And then we need some test vectors, a number of 4 test vectors here. For example, here we set milliseconds, seconds, hours, and minutes and hours to 0, and we expect after the update function that only the milliseconds are incremented. And the other tests covers the corner cases when the seconds, the minutes, and the hours had its wrap around. Run it, and then we need to set the variables to the target system. The first test case 1, sets this test case here, or these test vectors. We start the application and the trace. And sometimes I got this message here. I need to rerun this. Okay, then we get the code coverage result here for this specific test case, which is incomplete, of course, and then we can check the test against the good values. Okay, in this case, the test has been passed. We got the wraparound here with the correct results. Okay, this is only for one iteration. And we can put this into a loop for all the test cases. I have prepared this loop already. The only additions I made here to the single executed test is that I put here some weights for the results in. So we wait. The recording of the trace has been stopped. We wait for coverage coverage calculation is completed, and then we are waiting for the next halt and on the breakpoint for the next iteration. And then we do the evaluation of our test results, and in parallel to that, the code coverage has been calculated and displayed here. And if we start this, then you will see that we have cleared the coverage results from before. Then we do the steps here, and the calculation of the coverage is done right after each breakpoint was hit again and accumulated. And you see we are now finished, that there is still one not 100% covered code here, and we can look into it, and you will see that this is the we are missing the test when the seconds have its wraparound. So we need to add some one test case. I copied this one, and this should be at the seconds wraparound. So when the milliseconds are 9, and we expect that we increment the seconds. This is the missing test case here. So we add this test case, and then we did the coverage or the test again. And hopefully all the tests will be passed. Okay, all the tests are finished and passed, and we got the 100% code coverage for all the traced functions here. Finally, we can create a report. Also, there are some properties available for file paths, for the pattern, for example, to include source code, lines, etc. Create a report, and the report is automatically opened. And finally, we clean up everything, and we are finished with our test. Okay, then yeah, before I end this webinar, as promised, there should be a few words to say about dealing with optimized code. So you may notice that trace-based code coverage basically only considers the paths through the control flow that are actually executed, and that can be seen in the trace. If there are not taken branches present, the information about the existence must be taken from the control flow information. I said this before. So this control flow information is provided by the debug information in the ELF file, or you can look at the binaries to get these information. But these information may be incomplete, especially for optimized code. If we are looking on this example here, this is a simple switch statement with 5 case statements in it. If you compile this with some optimization settings, then the compiler may create a so-called jump table out of this case here, not not jumps to each tests and jumps to each or branches to each case block, but only one conditional jump to this jump table here below, and from that you jump back to the case labels. So as a result of this, we have only this indirect branch here. It looks a bit strange because of its ARM code here in this case, but you see that you change the PC here in this case, and you jump here with these address here to one of these entries in the jump table. The information how many branch targets actually exist can neither be determined from the binary code nor from the standard debug information. This is the reason that the approach of using trace-based coverage would lead into a wrong coverage result. In this case, we would get a 50% branch coverage instead of the correct 20% that we get with these 5 case statements here. So how to overcome this? With a specific compiler extension that is available for several compilers from different vendors, the missing control flow information telling the debugger how many branch targets we actually have can be provided to the debug tool. The additional information about the control flow is added to the debug section of the ELF file. With that, the binary itself, it's not changed. So the code that you are running is the same code that you are using later in the field. Only the debug information, which is not loaded into the target, it's only loaded into the debugger, is changed. So the runtime behavior is also not changed here. That's the important point here. If you if the debugger recognizes that the information, this control flow information is missing, then you get a warning here or a remark in at least in the coverage result or in the message log of UDE. So if you get this message, then you have to use the compiler switch. You have to look at the compiler documentation, which switch that is, to add the required control flow information in your ELF file. Okay, that's all for today. Time is up. With that, we end this webinar series, this small series of 3 webinars about specific aspects of debugging and testing with UDE. And all the webinars has been recorded and are available on the Germany Hitex YouTube channel or using our webinar webpage on pls-mc.com. If you have any questions about this webinar and about code coverage with UDE, then please drop us an email. Thank you very much.